In this video, we're going to discuss how to solve polynomial inequalities. So we've already talked about solving linear inequalities back in chapter 1. So the highest power on x was x to the first, but now we're going to have inequalities where we have x squared, x cubed, higher power terms of x. So if we think about the graph of a polynomial, we know it's a smooth, continuous curve. I'm just going to draw a parabola here, but this would apply to any polynomial function. So if we look at where it's positive and versus where it's negative, this one will be positive right here roughly, and right here roughly, because that's where it's above the x-axis. And then the polynomial will be negative where it's below the x-axis. So the points where it switches from positive to negative are these x-intercepts, because that's where it's equal to 0, and so it switches from being positive to negative at those points. So what we can do to solve a polynomial inequality is we can find the x-intercepts, which means we're finding the real zeros, and then we can check each interval around the zeros to see whether the function is positive or negative. So for example, for this function, suppose those zeros are at 1 and 3. We know that the function is positive to the left of 1, the function is negative between 1 and 3, and then the function is positive to the right of 3. So to check positive or negative, we're comparing the function with 0. Positive means greater than 0, negative means less than 0. So this means we'll need to make sure that one side of the inequality is 0, and then we will find the zeros of the other side. So for example, if we want to solve x squared minus x is greater than or equal to 20, we would want to make one side 0 first. So we could subtract 20 from both sides. And then we need to find the zeros. So probably the easiest way to do that here is to factor. So skipping the details here, this factors as x minus 5 times x plus 4. So the zeros of x squared minus x minus 20 are 5 and negative 4. Those are the x values that would make the left side equal to 0. And that means they are solutions because the inequality says greater than or equal to 0. So in this case, since we have that possibility of equality, those zeros actually are going to be two of the solutions to the inequality, because if we plug either one in, we get a true statement because 0 is greater than or equal to 0. So then what we need to do is we need to check these three intervals that we've created now on our number line. So if we pick a number, any number in the interval, and test it and see if it's a solution or not, then we will know that the same is true for all the other numbers in that interval, because the only place where the polynomial can switch sign is at the zeros. So the only place where it can possibly switch between being positive and negative is at negative 4 and 5 in this case. So for example, if we test a number in this interval to the left of negative 4, so we could, for example, test negative 5. So we could substitute it into our polynomial, and it doesn't matter whether we use the factored version or not. I think the factored version is a little easier because we can already see that both of these are going to be negative, right? We're going to have negative 10 times negative 1, which is actually positive. So it is greater than or equal to 0. So since we get a true statement, that tells us that negative 5 is a solution. And that means then all of the numbers on this interval are solutions. Next, we need to test a number between 4 and 5. So 0 would be an easy choice. We substitute 0 in. We have 0 minus 5 times 0 plus 4. So we have negative 5 times positive 4, which is negative 20. And that is not greater than or equal to 0. So since we got a false statement, that means that 0, the number we plugged in, is not a solution. And that means that none of the numbers between negative 4 and 5 are solutions. And then we need to check the interval to the right of 5. So we could use 6, for example. So if we plug 6 in for x, we get positive 1 times positive 10, which is greater than or equal to 0. So we get a true statement, which tells us that 6 is a solution, and then we know all the other numbers in that interval are solutions as well. So we can see from our number line here what the solutions are. All the numbers less than or equal to negative 4, and all the numbers greater than or equal to 5. And we usually write the solutions in interval notation. So we'd write the solutions for this one like this, including the endpoints at negative 4 and 5, because remember those numbers, when we substituted in, we did get a true statement because we got 0 greater than or equal to 0. All right, let's solve this inequality. We have x cubed plus 3x squared is less than or equal to x plus 3. So again, we need one side to be 0. So we'll subtract the x and we'll subtract the 3 from both sides. And so again, we need to start with what numbers make the left side equal to 0. So we would probably want to factor that left side. Since there's 4 terms, we can factor by grouping. So we can factor out x squared from the first pair of terms and a negative 1 from the second pair of terms. And then we can keep going. X squared minus 1 is a difference of squares, so that will factor further. So the zeros are negative 3, negative 1, and 1. So I'm going to need a new slide here. So I'll copy down our inequality up here. So we'll take those zeros and put them on our number line. And once again, in this case, the left side is allowed to be equal to 0. That won't always be the case. We'll do an example in a minute where it's not. But since the left side is allowed to be equal to 0, then these numbers that make the left side 0 are solutions. And then we'll need to test a number in each of these 4 intervals by substituting it in and seeing whether or not we get a true statement. So for example, for the left interval, we could substitute negative 4. So we'd substitute that in, we get a negative number on the left. So we would get a true statement because a negative number will be less than 0. So we have solutions there. So I'm going to skip the details of substituting the numbers in because I think that's something you can do. If we substitute a number here, so like negative 2, for example, we could use. You can use any number between negative 3 and negative 1. Negative 2 is probably the easiest. If we substitute that in, we actually get a positive number. We get 1 times negative 1 times negative 3. So we get positive 3, and 3 is not less than or equal to 0. So since it's positive there, we don't have any solutions between negative 3 and negative 1. We need to test a number between negative 1 and 1, so 0, for example, would work. If we plug in 0, we get 3 times 1 times negative 1. That's a pretty easy one. So negative 3, which is less than or equal to 0. So all these numbers are solutions because we got negative. And then if we test a number greater than 1, so like 2, we actually get a positive number again, so we have no solutions there. So we can see now from our number line where the solutions are. So we would want to write the solutions in interval notation. So we have negative infinity to negative 3, including the negative 3 because the left side is allowed to be equal to 0. And then negative 1 to 1, again including those endpoints as well. All right, let's do an example where the equality is not included. So suppose we have this inequality here. So now it's strictly greater than 0. So the numbers that make the left side 0 are not solutions, but they're still important because they separate the intervals where we have solutions from the intervals where we don't have solutions, because the only place the polynomial can change between positive and negative is at those zeros. So we'll want to factor this by grouping again since we have 4 terms. So I'm going through this part quickly since we've done this before. Feel free to pause the video if you want to copy all of that down. But this is how it factors. So our zeros of that polynomial on the left side are 1, negative 2, and 2. So I'm going to need a blank page again. So here's our polynomial. Our inequality says it should be greater than 0. So I'm going to mark our zeros on our number line, but now those are not solutions. If we plug in any of these 3 numbers for x, we get 0 on the left, and this statement, 0 greater than 0, is false. So these 3 numbers are not solutions. So I'm going to mark that on here with open circles to show that we're not including those as solutions, but they are separating the different intervals that we need to look at. So once again, we're going to test a number in each of these 4 intervals, and again, I'll skip the details. So if we choose like negative 3, for example, that makes the left side negative, which means we get a false statement. A negative number is not greater than 0. So no solutions there. If we choose a number between negative 2 and 1, say 0, we get a positive number, which is greater than 0. So a true statement means we have solutions there. We need a number between 1 and 2, so this one is not going to be an integer. We could use 1/2 for example, 1.5 for example. And if you substitute any number between 1 and 2, the left side does become negative, so we have a false statement, which means no solutions there. And then if we choose a number greater than 2, for example 3, that does give a positive number on the left, so a true statement. So this process was identical to the previous problem, except those zeros are not solutions now because we don't have that or equal to. So when we go to write the solutions in interval notation, we'll just need to use parentheses instead of brackets to show that those endpoints are not solutions.